So in this video we're now going to have a look at the important distinction between weight and mass. We saw from the last video that we had the principle of inertia that would said that an object's velocity will remain constant unless it's acted on by an external force. And this is the principle of inertia, and what we're going to see is that the inertia is the resistance to the changes of motion, and we can characterise that resistance by the property of an object known as its mass. Now, quite often we make a mistake between the distinction between weight and mass, so what we're going to do is we're going to illustrate this with an example. So let's consider a track with a minecart that's full of ore. Now, I'd like you to ask yourself the question, would you prefer to set it in motion when the cart is full of ore or if it's empty? I'm sure most of you will say that it's going to be easier to get it to start if we take the mass of the ore out of the cart and then give it a push. And if I was to ask you why, you may think that it's because the weight of all the ore inside is somehow pushing down on the railway track, and that's causing a resistance to the cart's motion and making it harder for you to set it in motion when you give it a push. If that's so, let me ask you the second question, which is, if the minecart is now actually in motion and you've now got to try and push against it to try and stop it, would you prefer it to be full of the ore or not? Now, if your thinking was right, then you'd prefer it to be full of the ore because it's pushing down on the track, and therefore this will help you to stop it. But of course you can see that you would prefer it to have no ore in the car or in the cart, because then it would have less mass, and if it's got less mass, it's got less inertia, and with less inertia, it's got less resistance to its change in motion. So you see, on that example, what measures the inertia of a material body is the quantity of matter, which is measured by the mass. And as we will see, this is very different from the notion of weight. So mass characterises the resistance to motion changes, and the weight is a force produced by an object inside a gravitational field. So if we come back to this first statement, we can write it more formally. I'm sure you remember from your GCSE days that a force is required, and if we multiply that by the mass, the force is equal to the mass multiplied by the acceleration. So what we can see is if we have a greater mass, therefore we have a greater inertia, so this force here will produce, on a greater mass, a smaller acceleration. If we come over to our second statement, weight is a force produced on an object inside a gravitational field, then what we can say here is that the weight of an object, let's get the pen, so the weight of an object is equal to the mass multiplied by the gravitational field. Now, because this weight is a force, if our object is accelerating in a gravitational field, then our weight and there's no friction, is equivalent to our force over here, our resultant force. So I can equate these two together, and that will tell me that F equals ma, and that's going to equal our weight, which is equal to mg. And now hopefully what you can realise will happen is that the mass will cancel from both sides, and that will just tell us that the acceleration is equal to our gravitational field strength, and hence all objects, no matter what their mass, if there's no air resistance or there's no drag forces acting, then the acceleration is always the same, and that acceleration is the value of the gravitational field strength at that point. Now what this equation here also tells us that if I apply a force to a mass, I'm going to get an acceleration. And if I continue to apply that force, then it will carry on accelerating, and it would carry on accelerating, and if I kept it going for long enough, I'd have no end to how fast I could make the object go. Now in reality, this isn't true, because you may or may not realise that nothing can travel faster than the speed of light. So this equation makes the assumption that the mass of the object remains constant. Now, this is a pretty good approximation, but in actual fact, what we should be talking about is that the mass of the object is equal to what we would call its rest mass, which is the mass of the object when it's not moving, divided by what's called the Lorentz factor, which is 1 minus the speed that the object is going squared, divided by the speed of light squared. Now, if we were to take this equation and plot it out on a graph, like so, where if I put a dotted line in at where the speed of light is, so on our bottom axis we've got v, and then on our vertical axis here we will have the mass of the object. Now what will happen is, for very low speeds, the mass of the object basically remains the same as its rest mass, but only when we approach towards the speed of light, then the mass of the object will increase hugely, and it will then asymptote at the speed of light. So what this actually tells us is that any object has got a rest mass, and if it was travelling at the speed of light, then at the speed of light we would have an infinite mass. And clearly this can't happen, so hence objects that have got a rest mass cannot travel at the speed of light.